All right, well, good Monday morning. Welcome to another beautiful day here in calculus. And just to let you guys know what my plan is, we're going to talk a little bit more about improper integrals. You may remember last time we were kind of in the middle of that, dealing with infinity. And really the only trick was we had to take a limit. But we'll go ahead and do some more of those today just so you can kind of see specifically the other type. We only got to one of the types. So I'll remind you about that one and then do the other type and then show you some kind of quirky things about them. And then we're going to move into the last chapter for this class, chapter 4. So we are in the home stretch, and chapter 4 is all about differential equations. And we'll talk about what those are and what those mean when we get there. But as always, I want to go ahead and open it up to you. I imagine there are probably some questions about homework, seeing there are a slew of them due this evening. What would you guys like to see from the homework sets? And I just realized I just coughed and I still like covered my face, even though I'm the only person in the room and you guys aren't here. Old habits. So no homework questions? You're kidding me. This is usually about the point where somebody comes in with some last minute ones.
Can we look at number 8 from the trig substitution one?
Sure. I'm going to put that on the list. All right, well, let's go take a peek at that and see how it goes. So let me share my screen and we'll go find that one. All right, trig substitution. Numero 8. Okay, so we've got an integral of x cubed times the square root of 81 minus x squared. All right, so what about this one suggests that trig substitution is what we want to use? Anybody see what it is about this form that suggests it?
It's the difference of squares.
Beautiful. Yep, there's a difference of squares, and specifically inside the square root, but difference of squares for sure is what would suggest wanting to try trig substitution. So let's just take a look at this guy. So we've got x cubed times the square root of 81 minus x squared. All right, so we've got a difference of squares. So that suggests that we're not going to use tangent. We would use tangent if it was a sum of squares. So this is either going to be a sine or a secant. And which one's it going to be? If we're going to do trig sub here, what's the best choice? Well, how about this? I know it's going to want to start with a 9. All right, and then Alexi just put in the chat box sine of x. Or, sorry, sine of theta. So the 9 comes from the fact that there's an 81 here. That's my a squared. So I want to have a 9 so that everything's going to simplify. And then I definitely want to use a sine because that's the form for the 81 minus x squared. If it was x squared minus 81, that's where we would use secant. So if you're still looking at those going, man, I have trouble remembering which one to use, think about the Pythagorean identities. Right, like go to the sine squared plus cosine squared equals 1. And think about what kind of form you get excuse me, when you move things around, right? Like if you solve that for cosine, whoops, said cosine and wrote it at the same time. If you solve that for cosine, you get 1 minus sine squared. And so remember, we're substituting in for our variable. So if you've got your a squared minus something squared, that's where you want to use sine. So that's one way you can kind of remember, because I know it gets tough sometimes where you're like, geez, there's so many different rules on how do I decide what. Just remember what we're doing. We're making use of the Pythagorean identities to simplify. All right, so we're going to go with x equals 9 sine theta. So then dx is going to be 9 cosine theta d theta. So if we substitute all this stuff in, we're going to get 9 sines of theta cubed times the square root of 81 minus 81 sine squared theta times 9 cosine theta d theta. So there are all the different pieces, but now hopefully we can simplify this a bit. The square root of 81 minus 81 sine squared theta is going to become a 9 cosine of theta. The 81 comes out as 9 from the square root, and then we have 1 minus sine squared, which from the Pythagorean becomes cosine squared. Square root of that is cosine. And then we've got the 9 cubed sine theta, so that's 729 sine cubed theta. All right, so let's pull all these numbers out front. I'm just going to write it as 9 to the 5th because I'm a little lazy right now. But that gives us a sine cubed cosine squared. All right, so we've made use of that substitution, and it's turned just into a trig integral, which now is going to suggest that we do a u substitution. All right, so what do we want to substitute in for here? So remember, the trick with these is to look at the powers. And we see we've got cosine squared, we have sine cubed. And the fact that that guy's odd tells us, as Adam just put into the chat box, we want to let u be the other one. So we're going to let u be cosine. So then du is a minus sine theta d theta, which means that one of these signs is going to be part of the du. The other ones we'll have to take care of with a Pythagorean identity, right? Because this is going to be the same as sine squared times cosine squared times, I was going to move it out of the way, bring that one out here. And then this sine squared, we're going to use the Pythagorean identity again, but you solve it for sine. That's the same as 1 minus cosine squared times cosine squared. So that's kind of the man behind the curtain stuff. So if we go and we do this substitution with our u's and all that, the minus sign is going to come out front. So we're going to get, I'll carry it on over here, minus 9 to the 5th times the integral of, well, 1 minus cosine squared is going to be 1 minus u squared. The cosine squared is another u squared. And then the sine d theta, that was our du. All right, so we have minus 9 to the 5th times the integral of u squared minus u to the 4th. Which is going to give us u cubed over 3 minus u to the 5th over 5 plus c. And now we get to have fun. We get to resubstitute. So if we go back and replace the u's, this becomes minus 9 to the 5th cosine cubed theta over 3 minus cosine to the 5th theta over 5. And then lastly, we need to substitute back in for the thetas. So here's going to be where we need to make our little right triangle. So let me erase this a little bit right here. There's our theta. We know that the sine of theta is x over 9. If you just solve that for sine of theta. So sine is opposite over hypotenuse. And then this third side, if we use the Pythagorean theorem, gives us square root of 81 minus x squared. And again, I think I mentioned this last time, that this, it showed, it came from our original integral, and it showed up again. Okay, so then the cosine of this, because remember that's what we're looking for. The cosine is going to be the square root of all that stuff over 9. All right, so let's put that into this thing, and we'll finally have our answer. Just make some space here. All right, so we have minus 9 to the 5th times, okay, so 1/3 times cosine cubed. So that's going to be the square root of 81 minus x squared over 9 cubed minus 1/5 cosine to the 5th. So square root of 81 minus x squared over 9 to the 5th. Plus c, and this will simplify if you distribute, and you can do a lot to kind of clean this up. However, I'm good with that.
I want to maybe chime in on like maybe a semi-philosophical note. This recurring in the triangle of the figure, the 81 minus x squared that was in the original integral.
Mm-hmm.
That's another one of those things that I like about calculus, where you see why things are the way they are. Like if that wasn't one of the sides of the triangle, then all this trig substitution wouldn't work, right? I mean, that's,
yeah, I don't know that I would say the trig sub wouldn't work, but it's a byproduct of using trig sub. You know what I mean? Like but it's also, I think what you're getting at maybe, and this is how I look at it, is if we start with this kind of thing, it probably should still be there, right? And but yeah, I think I'm with you though, that it's kind of nice how it all pieces together. You know, everything sort of makes sense at the end.
kind of the way that I'm looking at it, and the reason I said that is that looking at what we have for our x substitution of 9 sine theta, right?
Mm-hmm.
Like the 81 minus x squared is what it is as a result of, like, you know, putting these into this form of this trigonometric form. I don't know. Maybe it's a little early in the morning. I'm not like fully expressing myself here, but to me, it seems like one of those like self-evident things about, you know, where it's like, oh, this works because of this. Okay. Because every single time that you go to work out the triangle, you're like, oh, that other side is the thing that was in the original
Yeah.
All right.
Yeah. No, and it's all because of the structure, right? It was that fact that it was difference of squares that then that pushes everything, because the difference of squares shows up in the Pythagorean identity, and then clearly if we're using the Pythagorean identity, then the Pythagorean theorem has to apply, and blah blah blah, you know. So but yeah, and Adam just put, I get what you're saying, and I definitely do too. It's one of those like chicken and the egg things, right? Where you go, well, of course this has to show up because we did trig sub, but then you go, right, but we did trig sub because that was there, but that was there because we do the trigs, you know. So you can get into that roundabout, well, what actually is driving it? And yeah, I think the answer is it just is, because that's the structure. And to me, that's the beauty of math, that you can recognize a structure and then the structure just flows, you know. But yeah, no, I'm definitely on board with that too. Now, do you guys want to hate me? You want to hate me right now? You want a little check this out? We didn't have to do trig
Why
sub.
not?
Yeah, why not? It's early. It's Monday. We're at that point in the quarter. So check this out. We could have done this all without doing trig sub. We could have started originally. Let me rewrite it down here. We could have just done u equals 81 minus x squared. Because check this out. Du then is minus 2x dx. So we can reserve one of these x's for that minus sign. So when we substitute that in, we're going to get a minus 1/2. Now the x cubed, if we use one of those x's, it leaves another x squared. But that x squared, if I solve with this thing, is an 81 minus u. And we're going to get the square root of u du. So that's minus 1/2 integral of 8u to the 1/2, or sorry, 81 u to the 1/2 minus u to the 3/2. And that's a really fast integral, right? I don't even have to do any kind of trig anything. Let me clear up a little bit more space here. And once we do that, let's see, so we have the minus 1/2. We're going to get 81 times u to the 3/2 over 3/2, so times 2/3. Minus u to the 5/2 over 5/2, so 2/5 u to the 5/2. Yeah, plus c. But now when we substitute back in, remember what u was? U was the 81 minus x squared, so we're going to get 81 minus x squared to the 3/2. Well, that's that. And then 81 minus x squared to the 5/2, well, that's that. And then all the other stuff is what would remain after we simplify. So it turns out this one doesn't need trig sub. But if you didn't see that, then that's not the end of the world. I just wanted to point it out because sometimes, like I think this one was a little bit faster if we just do the one substitution. All right, and it's good to be able to recognize that, but if you don't, it's not the end of the world, right? Because trig sub will get you there. It's kind of like saying, well, I'm going to drive to Carson from South Lake, and you can just hop on 50 and go down the hill, or you can go around the lake up to the North Shore and then across Mount Rose and then come back down 395 and now we're back in Carson, right? So you still get there. It's just one's maybe a little bit faster than the other. And for those of you who are not from the Tahoe area, you have no clue what I just said. But all right, so cool for that one. I just see in the chat box here. So Bruno, you're asking about number 17. Is that from this section as well? Yeah. Okay. We'll go just take a real quick look at that. We might have done that, but we'll check. And then Adam, you said, can we do that if we recognize it and it looks easier on an exam? And when you say do that, you mean like the U substitution? Yeah. Okay. So on an exam, if I just say, hey, here's an integral and do it, feel free to do it any way that works. If I unless I say do this integral using trig substitution, then I'm specifically going to want to see it done with trig sub. But yeah, barring anything else, do it however you see it. See it works, right? And that's kind of that's why I show you multiple options, is to kind of train you so that later when you're doing this on your own, you can recognize the forms. Because let's be real, if you're doing something in your job where you have to integrate, right? So let's say you're an engineer and all of a sudden there's this, oh, I have to figure out the value of this integral. You don't know what section of the book it comes from, right? You don't know that it comes from 3.3, where 3.3 we're talking about trig sub. So, oh, maybe I should use trig sub. Yeah, I have no clue. You just have, here's an integral. And so using techniques from wherever we happen to have found them is definitely appropriate if they apply. And this is one where trig sub works, but also U sub. It'd be really easy to make this so that it isn't so nice. Like you change this x cubed to an x squared, and now U sub is going to be horrible. And what you get when you do the U sub is another thing that would require trig sub anyway. So, but I have the ability to see that because I've done a million of these, right? So I recognize the patterns. You're not there yet, and that's okay. But if you start seeing those patterns and go, ooh, no, this is a good one for U sub, totally go ahead and go for it. All right, so let's go take a look real quick at number 17 and see what that guy looks like. Yep, I think you're right. I think we did this one or something similar last time. But this is the one where we want to divide by the 16 minus x squared, because then we got our y prime equals, right? And so we know to get our y prime, we just have to do the integral. So it's going to be an integral of 1 over 16 minus x squared. And this is one that there are actually multiple ways of doing it. I would actually recommend using partial fractions instead of trig sub, but that's totally on you. So yeah, we definitely did one of these last time. So Bruno, if you go back and you look at the lecture from Friday, jump into YouTube and look at that. It should be near the beginning. So I am going to go ahead and defer to that. All right. So any other homework questions, or are we good to move on? All right, well, hearing none and seeing none, I'm going to hop up to the whiteboard. I'll be right back with you. All right. So if you guys haven't figured out, I'm actually at a new place, so things look a little bit different here. So last time we were talking about improper integrals, and the big thing about improper integrals is that for any of them, we've got some sort of deal with infinity, right, with our bounds. And so there were really the two types. The first one were the ones where one of the bounds is infinite. So we did a few of those. I'll do another one to kind of warm us up and remind us about how those work. So we have infinite bounds, and then the other type are going to be where the bounds are finite. And this is where the bound is an infinite discontinuity. Where there's an issue with plugging this bound in to the original function. All right, so like vertical asymptotes. So we'll get to that. You'll see what I mean when I get there. But let me start with kind of reminding you what it looks like when we have an infinite bound. All right, and I'm going to throw just a little bit of a wrinkle into it. I'm going to give us both of them being infinite bounds. Let's say we're going to integrate from minus infinity to infinity, 1 over 1 plus x squared. All right, so this is that type 1. So the trick to these, what we did was we basically said, well, I can't go to infinity, but I could go to some number, call it, say, b, and I could evaluate it out to a certain point, and then we could just let that point go to infinity, right? So like this is the trick. This is what we did. We did the limit as b goes to infinity of the integral from minus infinity to b of 1 over 1 plus x squared dx. Right? Because we know, okay, well, we can go ahead and anti-differentiate this, and then we can plug in b, and then see what happens as we go to infinity. All right, but I think you guys can probably see what's going to happen here. What's a little bit different about this one as opposed to the ones we saw last week? What are we going to have to do differently?
Infinity on both of the bounds.
Yeah, so since there's infinity on both, we're going to have to play the exact same trick here. We're going to need to turn that lower bound into an a. And this is the first time you've ever seen one of these. We're actually going to have a double limit. We're going to have a limit as b goes to infinity of the limit as a goes to minus infinity of the integral from a to b 1 over 1 plus x squared dx. And I know I just broke some of your brains. Oh, wait, what? A limit of a limit? Yeah, it's a limit of a limit. Basically, what you're going to do is you're going to do the one limit. Then, after you evaluate that limit, you evaluate the other one. All right, because our answer is going to have both a and b in it once we anti-differentiate, and then we can just evaluate those limits. It doesn't matter which order you do these. We can do the a one first and then the b one as I have it written, or could have done it the other way. It doesn't really matter. But here's how this is going to play out. All right, so let's anti-differentiate 1 over 1 plus x squared. Anybody recognize that? What's the antiderivative of that guy?
Inverse tangent.
It's inverse tangent. Good. So the limit as b goes to infinity of the limit as a goes to minus infinity of inverse tangent of b minus inverse tangent of a. So the inverse tangent was the antiderivative of that, and then I'm plugging in b and a as my bound. All right, well, let's see what happens there. Now, I don't know how well you remember your inverse tangent, so I'm going to help us out a little bit. the graph of inverse tangent. Let me do that over here. We'll actually start with the graph of tangent. So if we look at tangent, the piece that matters is the piece that's right around 0, and it did something like this. You may remember there were some vertical asymptotes. This was at pi over 2. This is at minus pi over 2. So this is the graph of tangent. So remember, inverse tangent is just going the opposite direction. So let's look and see what happens when we evaluate these limits. So let's think about it as b goes to infinity. We're looking for the inverse tangent of infinity, basically. So if you follow this graph and think about where we start getting once we get really, really big, our angles get closer and closer to pi over 2. So this one right here becomes pi over 2. All right, we'll do the same thing. Where do we go as we go to minus infinity? Our angles get closer and closer to minus pi over 2. So that's what that one's going to be. So we get pi over 2 minus a negative pi over 2. Well, if you add that all together, that ends up being pi. So the integral from minus infinity to infinity of 1 over 1 plus x squared is actually pi. It's a finite number, right? And so we call that a convergent integral because we get a value. But it turns out that that's a finite area. All right, so if you end up having both bounds as infinities, you actually have to do both limits. The limit is one goes to infinity and the other goes to minus infinity. All right, but if you want the truth of the matter, I never do limits. I just plug in infinity. I just plug in the minus infinity and I do the limit in my head. I don't actually write it out. So what you'll see me do if we have something like this, instead of doing the whole write out the limits business, I'll jump straight to the, all right, I know that's an inverse tangent. So this is going to be inverse tangent of infinity minus inverse tangent of minus infinity. Same kind of idea. I'm just plugging in the bounds. And then I go, oh, okay, so this is what gives me a pi over 2 minus the negative pi over 2. So I'm going to be lazy. This is totally Bruce laziness coming out. I don't want to write out the limit. It's too much stuff. So I'm just going to put in that infinity, but I'm not really putting in infinity because infinity it's not a number, right? So what I'm doing when I write that, that's my shorthand for take the limit as you go to infinity and see what happens. All right, so you'll see me do it like this instead of writing out the limits, but technically we're taking the limits because you can't plug in infinity. All right, so that was the first kind of improper integral, the kind where we're actually going to infinity. And it's funky, man. Sometimes you get finite values and sometimes you don't, right? Let me remind you with just this real quick example of one that doesn't converge, one that actually diverges. And I want to show you this one because there's something funky about it, something fun we can do with it. But let's look at this guy again. I think we did this as an example. I don't really remember because we did a whole bunch of different powers. But let's look at the integral from 1 to infinity of 1 over x dx. All right, so 1 over x, its antiderivative is the natural log. So you take the natural log of infinity minus the natural log of 1. Again, technically, it's the limit as b goes to infinity of the natural log of b minus natural log of 1. Okay, but now here's what I know about natural log. Natural log keeps growing forever, which means the natural log of infinity is infinity. And that immediately tells me that this thing is divergent. Okay, so I'm going to write divergence. So that means that the area underneath this curve from 1 to infinity actually grows without bound. There is no limit to it. It just keeps getting bigger and bigger and bigger and bigger. So again, what this graph looks like, think about 1 over x. It's the good old butterfly function. And so it's right. It's that. So what we just found is that the area underneath this curve from 1 to infinity, from 1 to infinity, is infinite. There's an infinite amount of area. Okay, so sometimes they're infinite, sometimes they're finite. There is no real rhyme or reason to it, and there are some patterns, but in general, you just have to do the integral and see what happens. Okay, but here's what I want to do with this one now. So remember this guy. Let's take that and rotate it about the x-axis. Let's actually just take this infinite wedge and let's spin it, and let's look at the volume of the shape that we get when we do that. All right, so let's just go with it. All right, so what's your initial guess? What's your thought? What should the volume be if we take an infinite area, spin it around in a circle? It should be an infinite volume, right? I mean, it only makes sense that it should be an infinite volume. Well, check this out. If we spin that around, we're going to get cross sections that are circles, right? So we're going to use the disk method here. So we need to have pi r squared. So the volume is going to be an integral from 1 to infinity of pi times the radius squared. Well, the radius is our function. So this is what we're going to get if we find the volume revolution. All right, well, 1 over x squared, if you integrate that, we'll pull the pi out front. The 1 over x becomes a minus 1 over x that we're evaluating at 1 and infinity. So that's going to give us a pi times minus 1 over infinity plus 1. The 1 over infinity, think about when we divide by a really, really big number, that goes to 0. So we end up with pi times 1, and all right, well, that's pi. Okay, now I want you to really think about this. Really think about this one, because this is crazy. Okay. We found out that the area under this curve is infinite. Right? There's an infinite amount of area. But you take that infinite area and you spin it in a circle, and you get a finite volume. What? Yeah, there's a finite volume. Okay, now you want to get really crazy. We're not going to do this because this example would take a long time. We could do it. It's possible. Look at the surface area of this. So you remember surface area, they get a little 2 pi RL business, right? If you set the integral up, do the surface area of this, you find out that that's also infinite. So we've got this solid with a finite volume but whose surface area is infinite, and whose I guess the shape of the or the area of the thing that we spun around to create the volume is also infinite. Yeah, this should hurt your brain a little bit. Infinity's weird. Infinity's incredibly weird, and all kinds of strange things happen when you deal with infinite integrals. This shape, actually, this volume, it's called, it sounds kind of like a black hole. Yeah, maybe, I don't know. But black holes are, yeah, definitely weird things too. This shape, it's called Gabriel's horn. Because if you think about it, it kind of looks like, if after you spin this, it's going to look like a horn, like a trumpet, but it's infinitely long trumpet. So it's the kind of instrument that could only be played by an angel. And there's the angel Gabriel. So that's why this is called the Gabriel's horn. But yeah, it's a funky thing. Here's the other funky thing. Think about this. So surface area is infinite. He's got to trust me on that. I don't want to blow through the math. But the surface area is infinite, but the volume is finite, which means if you wanted to, you could fill this thing with paint. It's only going to require pi gallons of paint to fill it. But if you wanted to paint the outside of it, there's not enough paint in the world. Wait. So you can't paint the outside, but you can fill the inside with paint. Oh, yes. Anyway, so these infinite things are really weird, but do they converge? Do they diverge? You really just, you got to do the math, because if you ever try to go with the, well, it should be this way, that's going to get you, because infinity, there is no following that should be. All right, well, so there's type 1, or the first type of these integrals. So let me show you one of the other ones. So the other issue that we can have with integrals would be kind of like on this picture. What if we were going to say 0, right? So I'm actually going to take the same function, 1 over x, but instead of going from 1 to infinity, let's go from 0 to 1. So I'm going to change my picture a little bit. Now I'm looking at this area. So we'll make it the blue area. Right? So what about this? Now, in this case, the 1 is no problem. 1 is beautiful. Everything's great there. But 0, we have a bit of an issue, because 0 makes this function undefined. You can't do 1 divided by 0. We've got this infinite asymptote, and we have that same kind of problem that we saw before of we keep adding an infinite amount, right? Think about what we do when we do integrals. We're splitting it into rectangles. Now those rectangles all have finite width, but now the ones closer to 0 are growing bigger and bigger and bigger. And as we make more of them, those smaller rectangles get yet even taller because of the going to infinity. So we have kind of the same issue of we're adding up forever, but those things that we're adding up just get bigger and bigger and bigger. It's still going to be an infinite interval. So the trick with these is exactly what we did before. Now I'm going to write it out the long way this time, and then from here on out, we'll just do it the fast way. But basically, we're going to do this. We're going to say, let's change that from a 0 to an a. Because if I just go from a to 1, where a is any number in here, no problem. But then we'll let a go to 0. So it's exactly the same kind of idea. This is probably going to make you a little bit happier because these are now non-infinite bounds. But if we're going to be really good about it, they have to be one-sided. So I'm going to put a little plus on there saying we're coming from the right. because that is what I'm doing. I want those a's to be on the right side of 0 coming into 0. So technically, they're one side of the limit. All right, well, now in terms of actually doing it, we're going to do what we've always done. So this guy's going to give us 1 over x. Its integral, again, is the natural log. So it's going to be the limit as a goes to 0 from the right of the natural log of 1 minus the natural log of a. Okay, so the natural log of 1, no problem. That's just 0. But the natural log of a, if we do the natural log of 0, this goes to minus infinity. As you plug in numbers closer and closer to 0, the number that comes out of the natural log gets more and more negative, blows up. So because that limit doesn't exist, we can go back to this guy and go, all right, so this diverges. So it turns out that this one has an infinite amount of area between 0 and 1. It also has an infinite amount of area from 1 to infinity. So it's another divergent integral. All right, well, that's just how 1 over x works. You change that to something else. Like if we did this same integral from 0 to 1, but did say 1 over the square root of x, that one's going to converge. You're going to get a finite value. So it really just sort of depends, what are we doing? Okay, so this is the second type where one of the bounds ends up leading to infinite growth. So we have to do the same trick of evaluating a limit. All right, so then we can have lots of fun and do something like this. What if we did the integral from 0 to infinity of 1 over x squared? Now, I say we can have a little fun with this because this is actually both kinds of integrals. You see the infinite bound. That was the first type we looked at. But the 0 is also coming from a vertical asymptote for 1 over x squared. So it's the second type as well. So it's actually a combination of both. If we were to draw the graph of this 1 over x squared, at least the part we care about, which is the 0 to infinity bit, it looks like this. So literally what we're doing is we're trying to find the area in the first quadrant underneath this thing. So we're trying to find the area of the wing, basically. All right, well, the fact that it's got both types doesn't really change anything. We're still going to anti-differentiate. We're still going to plug in bounds. And then we're going to do limits. So I'm going to be lazy about it. Integrating this is going to give us minus 1 over x that we're going to evaluate at 0 and infinity. So that's going to be minus 1 over infinity plus 1 over 0 from the fundamental theorem. Okay, now technically I'm not plugging in infinity and I'm not plugging in 0. Now I need to think about the limit. So what happens when I have 1 and I divide by something really, really, really big? Well, that guy goes to 0. All right, and then what happens when I do 1 divided by something really small? Well, if I divide by a number that gets closer and closer to 0, that number blows up. So that guy goes to infinity. So we've already seen those limit forms. So now we're just making use of those limit forms. All right, well, I get 0 and then I get plus infinity. Well, that tells me that this diverges. So it's divergent, which means there's an infinite amount of area under that curve. All right, so the moral of the story with improper integrals is you never really know until you actually do it. Are you going to get a finite value? Are you going to get an infinite value? No clue. And there is no logic to it. Like you might look at this one and go, okay, this is 1 over x squared. It's symmetric, right? It's a symmetric function. If you think about drawing this line in here. And yet on the one side, we get finite area. On the other side, we get infinite area. Right? It doesn't make sense logically. Infinity is not logical. It just isn't. Okay, don't try to apply logic to infinity. It doesn't work. You need to just run with it, do the numbers and see what's going on. All right, so we just do an end around. We say, well, we're not going to go to infinity technically. We'll stop it at someplace B, and then we'll see what happens as we go towards infinity. That's the workaround for the mathematicians. But then, yeah, okay, so now we can find. So then you might be asking yourself, well, is there actually a use for this? Like, who cares about finite area, infinite area, in going to infinity and all that? We care about it not as an area question, but there are all kinds of situations where we do want to add things up to infinity. In physics, for example, let's talk gravitational fields. I don't remember who it was, threw something in the chat. I think it may have been Adam about black holes. If we look at gravity and you want to find, the effects due to gravity, you have to go to an infinite bound. You definitely have to go out to infinity because no matter how far away you are, there's always a little bit of gravity pulling on you. Like right now, all of you are being tugged on by Jupiter. It's pretty small compared to what the Earth is doing to you. That's why you're not getting, pulled towards Jupiter. But there's a little bit of a tug, and Jupiter is really far away. Well, I mean, you can go even further away, go out to the stars, right? Take even the closest star other than the sun, right? Proxima Centauri. It's still like 4 light years away. It's tugging on you. Pretty small, but it's still there. So an example where you would need an infinite integral would just be something as simple as figuring out gravity and gravitational effects on an object from something else. So there are lots of applications where we do integrals to infinity. They're never area. They're never area. They're never arc length. Right. So like this whole Gabriel's horn thing that I showed you, yeah, that's not a real application. It's kind of fun because it shows you the infinity is weird thing. But actual applications, there are lots where we do go to infinity. Anyway, now I feel like I'm preaching. So hold on a second here. Okay, thanks, Bruno. Hopefully you got your question answered and everything's good. All right, so there's improper integrals, and that's the last thing that we really need to talk about when it comes to integration. So now think about where we are. We've learned what integration is. We've learned what we can use it for. We've learned, oh my goodness, all kinds of different techniques for actually calculating integrals. And I hate to break this to you, but what you've learned in terms of integration techniques is a very, very small, slim number of techniques. In fact, most things can't be done integrating it the way that you've learned. It's actually a much more complicated thing. Integration is tough. And in fact, there are a lot of things you just cannot integrate. That's not the case with differentiation. Differentiation, you can always differentiate as long as it's a continuous function. But anyway, we save those weird, quirky things for later. So if you're going to be a math major, you'll see that kind of stuff later. If not, you know, it's all good. You've learned what you need to learn in terms of integration. All right, so the last chapter that we're going to talk about is kind of another application of integration, and it's a topic that's called differential equations. Now, differential equations is such a big topic that we actually offer a class, a standalone class called differential equations. If you continue on in our sequence here at Lake Tahoe Community College, you will take that next year. That's the last quarter. So you take that in the spring quarter of next year. But even that class is only part of the story when it comes to differential equations. So there are more standalone classes that you take as you go further. So differential equations is actually a really big topic, but we're gonna just kind of dip our toe into it. So I want to start today just by giving you kind of well, what does this mean? What are differential equations? What exactly are we looking for? And all that. All right, well, here's the good news. It's exactly what it sounds like. They are equations that have differentials in them. And differentials, you may remember, are the little like dy's and dx's and all that. So really, what a differential equation is, this is just equations with derivatives. So anytime you have an equation that involves a derivative, it's a differential equation. So let me give you some examples. I'll show you some down here. So some examples of differential equations. You could have y prime equals 2x cubed minus x. Okay, so it's an equation equals with a derivative. It could also be something like this. We could have y prime minus 2y equals 1. So notice that again, it's an equation with a derivative, right? It could also be something like this guy. Let's say we have y double prime minus 3y prime minus 4y equals 0. So again, it's an equation with derivatives. Now notice that this one also has second derivative. Well, that's okay. In fact, differential equations, you can have any kind of a derivative in there in any kind of combination. So they can take on all kinds of different forms, but basically differential equation just means there's an equals and there's some kind of a derivative. First, second, third, fourth, maybe multiples. Doesn't really matter, but this is what these look like. Okay, so cool, differential equation. Now, the goal of differential equations, no matter what the equation is, the goal is to find the function. Okay, so your goal is to find y. Find out what equation is it that actually satisfies this equation, or this, what function satisfies this equation. Okay, so that's always the goal, is to find that function. All right, so what does that mean? Well, equation solving, or a function that solves a differential equation, means that if you were to plug it in, you would get a true statement. All right, so like for example, this first one, a solution to this. So I'm going to make we'll make a column here with the solution. All right, so this is a solution to this equation. it would be 1/2 x to the 4th minus 1/2 x squared plus 1/2. That's a solution to this guy. And you can see that just by plugging it in. Plugging it in means find the derivative and see if we get truth. Okay, well, the derivative of this would be 2x cubed minus x plus 0, which 2x cubed minus x plus 0. So therefore, it is a solution to this guy. Let's just jump down to the bottom one. Here's a solution to this guy. How about y equals e to the 4t? Let me show you that it is a solution to this differential equation. So to check this one, we'd actually need to get the derivative and the second derivative. So let's get those real quick. It's nice and easy because this is a e business. So y prime is going to be 4e to the 4t. And y double prime is going to be 16e to the 4t. So let's plug those in and see that we get truth. All right, so we need y double prime. So that's 16e to the 4t. Minus 3 times y prime, so minus 3 times 4e to the 4t. Minus 4y, so minus 4e to the 4t. Right? So I just plugged all those things into this equation right here. Well, 3 times 4 is 12. So 16 minus 12 is 4. 4 minus 4 is 0. So we get 0e to the t, which is 0. So that is definitely a solution to this differential equation. So this doesn't really help us in terms of finding the solution, but at least you can see how you can confirm a solution. You can see if you're right, and this is always a good thing to have, right? I'm a huge fan of having the, how do I know that I did it correctly? Is there a way to check? And with differential equations, there's always a way to check. Once you have your solution, what you think is your solution, you can always plug it back in and see if you get truth. Okay, so that's kind of nice, but there's always a, well, there's a way to actually check yourself. All right, well, the goal is to find y. Well, that's why we have entire classes on differential equations, to help us find techniques to actually find them. There's one more thing I want to mention before we start talking a little bit about how we find solutions. Well, actually, two more things we have to talk about, some terminology. All right. So every differential equation is classified in certain ways. There are certain ways that we describe them. And one of the things that we use is what we call the order. All right, so every differential equation has an order. And what this is the highest derivative in the equation. I'll put highest order derivative. So if you come back and look at these examples, this first one, this is a first order. Because we've got the first derivative, and that's it. This second one is also a first order. Because again, only the first derivative. But this last one that I wrote down here, this would be a second order, because it's got a second derivative. Okay. So classifying differential equations by order is kind of like classifying polynomials by degree. Right? Polynomials, their degree is the highest power of the variable you see. Well, the order of a differential equation is the highest order of the derivatives. What's the one that we go furthest down the line, right? So this one's a second derivative compared to a first derivative compared to the regular function. Well, second derivative makes it second order. Now, this is going to matter because the technique that you use to solve differential equations, we use the order to help decide what to do. All right, so it's just one of those things that we use this to push us in the right direction. All right, so that's order. But then when it comes to solutions, there are actually two kinds of solutions. So I'm going to put here for solutions, we've got general and we've got particular. And I think to show you the difference between general and particular, I want to come back to this first one, this first example that I put up here, the y prime equals 2x cubed minus x, because you guys can solve it. You already have the techniques to solve this guy. What are you going to do to get y for this differential equation? You guys see what you can do? Yeah, just integrate. That's exactly right. Because think about what this is saying. I want a function whose derivative is 2x cubed minus x. Well, that's exactly anti-differentiation. So if you were to solve this, you would get y equals, okay, so we take x cubed, make it x to the fourth over 4. That's our 1/2 x to the fourth. The x is a minus 1/2 x squared. And then, of course, we put on our plus c. All right, so just real quick. You already know how to solve some differential equations. You just do. You know how to solve differential equations that have only a derivative. So like only y prime or only y double prime or y triple prime. As soon as you start throwing other things in there, like remember that next one was like y prime minus y equals 1 or something like that. That y prime and y together make it so that we have to try different things. But yeah, we can actually, you know how to do some of these already. All right, well, this guy gives us the plus c, and this would be the general solution. Think of general and the word generic, right? When we find general solutions, we're finding the generic. What does this look like? Well, it's going to look something like this. The particular solution would be where we choose the value for c. And so you may recall that when I first gave you an answer, I think, if I recall correctly, and I might not be recalling correctly, I think I made that a plus 1/2. This one would be a particular solution. Because now we've chosen the value for c. It's not, well, any old c anymore. Nope, nope, it's a specific c. So when you were doing integral problems before, we're saying, hey, find this function. If you ever just left it as a plus c, you are actually solving the differential equation and providing a general solution. But then if you went ahead and calculated the C value, you were actually finding a particular solution to that differential equation. You were finding the one function that worked, not the general class of functions that works. Okay, so that's the difference between general and particular. So refresh my memory. What did you have to have in order to solve for C? When you did this before, what did you need to find the C value? All right, so thanks, Adam. That's good. So we needed a given value, right? We needed to have an initial value. So remember, we called those initial value problems. So the same kind of thing is going to happen here. You're going to always be able to find general. Like that, when we talk about techniques of solving differential equations, we're going to talk about techniques for solving general differential equations. But then in order to find the particular solution, what we're going to need is an initial value. So let me just put that down here. So need initial value. So in order to find the particular, you need to know an initial value. And so we actually call those initial value problems. Let me just write that up here as well, so that when you run across that in your reading or I say it, you know what we're talking about. Okay, so an initial value problem which, just so you guys know, I will always write IVP because I'm lazy, right? But initial value problem, it's going to consist of two things. So one, it's going to have the differential equation. And then the second thing that it's going to have is information about your function. And I want to leave it here as information about the function because it's not always an initial value, right? Sometimes it is. Sometimes it is the, well, this is what we know we get when we plug in 0. But it could be the value of a point somewhere else. It might not even be the value of a point. It could be something we know about the derivative of it. Think back to when you, remember when we did those where I gave you an acceleration and said find position? So we integrate once to get velocity and then we integrate it again to get position. In order to get that, we needed not just a position, we needed to know something about the velocity. So if you go back and you look at those, it was always given the initial velocity was this and it starts at this place or whatever. So that was information about the function that wasn't necessarily a point. So that's why I like to just write it as information about the function, because that can take all kinds of different forms. But you need something in order to get a particular solution, in order to find that C, right? Otherwise, the C can be absolutely anything. All right, so this is what they are. This is our goal. So we should probably start talking about how we do this. All right, well, let's start with ones you actually already know. Because you actually know how to solve some differential equations because we've been doing it this entire quarter. All right, so here are techniques, or here are ways of solving differential equations. All right, so what I'm going to do is I'm actually going to put here in a column form, and what I mean here by form is what the form of the differential equation is. And then over here, we're going to put what technique we use. All right, so the first form is y prime equals a function of x. So that would be like the one that we just looked at, where we had y prime equals, and it was only x's. All right, so the technique for that is just to integrate. So we're just going to find the antiderivative. So y is going to equal the integral of f of x dx. Now, we've only done a couple hundred of those this quarter, so I'm not actually going to show you any more. Because every time that you've done a here's y prime, find the y, every time you did an integral, you were solving a differential equation of this type. So that's actually why we talk about differential equations at this portion of the quarter, because you've been doing it. You might as well just now tell you what you've been doing. All right, so cool, easy peasy. All right, but they're not always this easy. And so the next form that you actually already know is a form that looks like this. Y prime equals k times y. All right, so notice that this is still a first order differential equation. There's just a first derivative. But this one's a little bit different because now there's also a y. And it turns out there actually are no x's whatsoever. But do you recognize this? You guys remember seeing that before? Anyone know what kind of function we got when we had this form? Yeah, Adam, it is PERT. This is exponential growth. Right? So this technique, I'm just going to put here exponential function, or just exponentials. I'll write below it what the solution was, but this was the y equals CE to the KT, or PE to the RT, or however you want to think about it. Yeah, so this is the PERT formula. We saw this, the function whose derivative is multiple of that function was an exponential guy. And again, this is the general form. That C right there tells us it's the general form. And we were able to find that C if we knew something, right? If you go back to that exponential stuff, we had to know how many bacteria cells we started with. We needed to know how much money was in the account. We needed to know whatever. But if we had a little bit of information, then we could actually find the C. Okay, so you've also seen these. I just wanted to bring it back because some of you may have forgotten about it. But we really were solving a differential equation. Okay, so now I'm really going to make you think back. Anybody remember how we got that as an answer to this differential equation? And it's okay if the answer is no, because that doesn't surprise me, because it was a long time ago and we kind of blew through it. And part of the argument was we just went, well, what kind of function has its derivative that's itself? And that, led to exponential. But let me show you how we actually came about with this answer. So I'm pretty sure I showed you this before. If I didn't, well, now you'll see how this works. But take that dy, or that y prime, and we could have written that as dy dt. And if you do a little bit of algebra, you get dy over y equals k times dt. And then once that we're here, this is where we integrated both sides. So the integral of dy over y is the natural log of y. The integral of k dt is kt plus some constant. I'm going to call it C1. And then if we want to solve for y, we just have to do change this to exponential form. So we get y equals e to the kt plus c1, which is e to the c1 times e to the kt, using the rules of exponents. And then since c1 is an arbitrary constant, e to the c1 is an arbitrary constant. And that's what led to that solution. So again, I'm just kind of bringing this back to show you that there was a process. That's how we came up with this. It isn't magic, but that's how we knew that the solution to y prime equals ky is y equals ce to kt. Okay, so hopefully that just kind of reminded you a little bit of how we do this. All right, well, this technique with the whole integrate both sides is actually a big one that we use all the time. And we call this separation of variables. So this technique right here. Separation of variables, because if you look at it, there are two variables here, right? There's the y and there's the t. And what we did through the process of the algebra is we made it so that one side had all the y's and the other side had all the t's. So we literally separated the variables into the two sides. Again, mathematicians naming everything what it is. All right, so if you've got a differential equation where we can do this, where we can actually make it so that all of the variables are on one side and we separate them out, we can integrate both sides. All right, now, sometimes that's easier said than done. It usually requires lots of algebra, but it's a great technique if you can do it. But looking at our time, we definitely don't have enough time to really start getting into this. So here's what we're going to do. We're going to go ahead and call it here. But next time, I'll show you how we do separation of variables, how to recognize that a differential equation is what we call separable. Guess what separable means? You can separate it. Okay, so if it's separable, we'll kind of use this technique to find solutions. And that's how we'll do, you may remember I gave you like 3 different examples. That's how we'll do the second one. We'll actually see how we can find a solution to that guy using separation of variables. All right, so with that, I'm going to go ahead and call it a day. So don't forget a couple things. There are homework sets that are due tonight. The last one, I don't know, is improper integrals in there? I don't remember if I moved that to next week or not. No? Okay, so cool. I'll move that to next week. So don't have to worry about the improper integrals, the ones with infinite bounds, but you guys can definitely start doing that if you want. But make sure you get the other ones done tonight by midnight. And other than that, I'm going to wish you guys a great couple of days, and I'll see you on Wednesday. So improper integrals isn't on the exam. No, I don't know. I should probably decide that, huh? Seeing the exams on Friday. Let's go with no. Let's go with no. It's not going to be on there. So the exam is going to be up through and including the partial fractions. I think that was the last technique we did prior to that. So whatever the homework sets, the last homework set due tonight, which is I think the improper fraction, that's how far, or partial fractions, that's how far the exam is going to go. So on Friday, if you want to start getting ready,
The exam is going to go through that, and then it's going to go back to where the last exam left off, which was somewhere in the applications. Unfortunately, I don't know what that is off the top of my head. Yeah, I'll let you know for sure on Wednesday. In fact, I'll send out a Canvas message today to let you guys know how far back the exam's going to go. But it's going to be wherever the other one left off. So I just don't know off the top of my head. But I'll get that message out in the next little bit here, just so that everybody can prepare for it. All right. So with that, have an awesome couple days, and I will see you all on Wednesday.